let me introduce, how many of you have heard of deep learning? Wow, that's pretty deep. That's the largest show of hands for. How many of you have heard of logistic regression? Yes. So deep learning is about 80% of logistic regression here, which is pretty high, actually. I'm a student of deep learning or neural nets 20 years ago, and they've come back with a vengeance. They call it the sine curve of neural nets, right? So every 10 years or so, they become popular. Anyways, we had a chance to reinvent neural nets again in a deep way. And so Arno here implemented deep learning in H2O. Before that, he was at Skytree doing, was founding engineer building most of their algorithms, which we don't know what he did there, but probably successfully, right? It's a great product. It's a good product that he built there. Before that, he was at Stanford Linear Accelerator, where he definitely showed some tremendous amount of HPC work, lots of algos, a decade of physics. So when he first showed up at H2O, we wanted a physicist. He was the physicist, and that is his title, physicist and hacker at Hexdata. So it's with tremendous joy I introduce Arno, and he'll spend the next hour and a half, probably needs a break, bio break sometime within an hour, but talking about algorithms, both deep learning. We're also talking about anomaly detection, unsupervised learning, and the whole shebang, right? So feel free to interrupt with questions, but it's hand-led as well. I would encourage him to probably do a little bit presentation of what de-hype the deep learning space a little bit. But without further ado, Arno Candel.
Thank you, Sri. I'm going to briefly go over my slides from last Friday at MLConf. Has anybody been there, actually? Okay, just a few. It's going to be just 2 or 3 minutes to give them the broader audience an idea of what deep learning has done in our context here. So basically, this is teamwork, okay? There's no single person implementing deep learning on a distributed Java platform that just works on any data set, that just runs on a cluster and just produces numbers that are great. This is a teamwork, and we have great advisors. Some of our advisors actually said deep learning is not that great, and that brings a good point up because you don't necessarily need deep learning for everything, but for some things, right? You have to learn what's good for what. And this tutorial today is going to do that, I hope. The goal is to give you an idea that there's more than just one method, but the focus now will be to introduce you to the range of tools we have. And of course, my emphasis is going to be deep learning. As you can see, deep learning is something that's multiple stages of nonlinear transformations. And it's different than a linear model because a linear model does not have these multiple nonlinear transformations. And that's also the difference to the old school neural nets. So a deep learning in our context is still a neural net, but it's a multi-layer neural net. And SVMs, kernel methods, classification trees, random forests, gradient boosted trees are not deep because they're not multiple layers of nonlinear transformations. You're still asking, what's your income, what's your age? And then you say, if income this and age that, then go there. You're not actually making income square minus age or something as a new feature. And that's what deep learning is doing, okay? So that's the idea here. In H2O, deep learning uses the same great platform that all the other algorithms are using. It's distributed, it's multi-core, it's obviously made for you, right? It's designed to handle real data, categoricals, missing values, lots of labels, different classes, output classes, for example. So much data that doesn't fit on any single node, but as a distributed system, it can still work. All these kinds of things are handled by the system. There's also adaptive learning rates. which make the training very easy. You don't have to specify the training, learning rate, any annealing, momentum, all of that you don't need. So any of you that still remember those issues with neural nets, you don't need to know them anymore. And all those that don't know that, just don't worry about it. It's basically the same as a random forest. It should just work. There's a couple more tuning parameters, and I'm going to tell you how to search through that tuning parameter space to find a good model. But the idea really is that it just works. So the design of it is that it's distributed, so that means one model that is initially created by random numbers. Let's say in the very beginning you have a bunch of random numbers, that's your starting model. That gets spread out to the cluster, and every node trains the deep learning model on the data that it has and gets better. So then you have, like, let's say in this case, 4 smarter models, and those 4 models get combined again to one good model that's hopefully better than any of the 4 alone, but doesn't really have to be. It's kind of an iteration, and after a long time of repeats of these cycles here, you'll get something that's good, because those 4 different nodes, they don't make the same model. They all make a slightly different model, and you average them, you get a little bit of generalization. It's basically like preventing overfitting while it's training faster. So it's a good combination of using the machines for something that's good for speed and good for machine learning. And at every one of those MapReduce iterations, at the end, the model that's made by these multiple models, the average of those, is being put into the key value store. So you can look at them from R, from the GUI, from the web browser. So basically, there's a state that's easy to debug for me, right? It's every time there's such a process, this map and reduce has happened, it's basically a consistent model. And I can just ask, how good are you? I can make a prediction with it. I can score it. As it's running, I can go and say, let's score the model right now. It self-scores itself during training, so you can always see how good it is. But you can also go and do it yourself, because it's just a model like any other model. You don't have to wait until it's done, which means it's online training, right? You can stop training at any point, and you can continue later. So basically, this whole thing is meant to be as user-friendly as it gets. And the results that we've shown in the past, this is the Higgs data set. We don't have to go into too much detail because we're looking at it later again, but basically the numbers are much better than with any other method. For MNIST, we got the world record number, 87 here, and actually it's now 83. I just posted that a few days ago. I actually ran a model that has 0.83% test set error on the 10,000 test set, which is as good as the Microsoft world record. As far as I know, there's no better MNIST results published. That's without convolutional layers, without distortions, without pre-training, just looking at 60,000 and 10,000 and making a model from the 60,000 and then predicting on the 10,000, right? So we got to 83. I'll show you that as well later. We have a Java model of all these models, so random forest, GBM, deep learning, all these models, you just export them to a Java file and put them into production with the click of one button. eBay was doing some text classification that was 8,000 columns, 500,000 rows. It's not too big, but just to show you there's 467 output classes. That would take quite a long time at random forest to predict which class it is, if you have to do this or not, this class or not, this class or not. It's easy with deep learning where you just have 467 output units that each get a probability. And actually when we run this, the hit ratio at K1, which means that the correctness of the highest probability to be the actual label was 90%, 88.4. So out of all these labels, it finds the right one quite often, right? So this doesn't mean a lot because you don't know what the reference value is, but it's a good result, and it shows that you can apply this to thousands of columns. So earlier we said 1,000 columns is a limit or something. 10,000, it seems to work just fine. Actually, the limit is just smooth, right? At some point, it just costs a lot to store this frame in this system because we, as Tom mentioned earlier, or Cliff, we store these columns, these vector features into small pieces. And when you have a lot of columns and you have a lot of pieces, you have a lot of little pieces in the whole system. And once you have many, many millions of little pieces in the system, when you're asking for one of those pieces, you have to look up which one it is, and there's some overhead there. So we have to redesign it in a way that you have multiple features at once, for example, that you get a whole block of the data at once instead of just a single column. There's things like that that can be done in the system to make it better. But for now, just know that it works, and if you have an issue, just ask us and we can help you. Typically, there's always a solution. This I'll go into later, and for Higgs, I'll also go into later, but you can see here there's numbers published by a Nature paper that say, up here's a table, they got to 88 AUC. You all know what an AUC is? Who does not know what an AUC is? It's the area under the curve. Basically, you want the curve to look like this in this square corner and not something round. And the area under this square thing is 1. The area under something that's less edgy, let's say more diagonal, is only half. So the AUC goes from half to 1 as you're getting smarter, so to speak. And the Higgs detection quality was 88 using deep learning. That was a major breakthrough in particle physics, machine learning, and only thanks to deep learning this was possible. And you see that neural nets and boosted decision trees only got to 0.73. So that's a pretty big difference, and that's because deep learning makes up features on its own. And those features are actually features that are physics features, formulas. Square root of this squared minus that squared, right? And if you don't know to make this formula on your own and write it down and like evaluate it and add it to your data set, you would never know. So you need a domain expert to come up with that formula and tell you you need this feature, or you need deep learning. And you see that deep learning got to an 88 here. And the complete feature set that was humanly made with these extra features got to also 88. So you can just make it up yourself once you have deep learning. So this was kind of the essence of this paper. And we also reproduced these numbers here for 3, 4, and 5 layers. And that was just on a weekend, right? I didn't have as much time as the Nature paper publication people that spent a lot of time running GPUs. This was run on our little cluster here. So it shows you that you get good numbers if you spend a little bit of time tuning. And in this case, it's actually a simple model. It's just default activation function. I just added a little bit of L2 penalty, but you don't really have to, and run it for a few hundred epochs. That's it. So pretty much anybody can just do this. There's a deep learning booklet that you have. Many of you have it already. If you don't have it, you can download it or get one copy over there. It explains all the options in deep learning. We also have one for R, how to use H2O from R. So whoever doesn't have this should get one fairly soon, and then make sure that you don't miss anything, because sometimes even I forget something smart, something useful, and then I say, oh man, had I only had that, you know. So it's important to make sure that you know what tools you have, because we're only adding the documentation effort now, but there's a lot that we could help you with. Yes, there's a question? How deep learning avoids overfitting if the data is small, yes. There's a couple of things. You can do L1 or L2 penalty, and then there's also dropout. And then there's the multi-model averaging that generally also helps, because you have 10 models, let's say, from 10 different nodes. They're all different, and then you average them. You get something that's not quite in the same local minimum, right? And then you have multiple of these averaging. So these are the things you can do. So there's a lot of work left to do, by the way. But before we go there, there's also work left to do in the data science field. So if you have, who is actually participating at Kaggle here frequently? How many? See, everybody? So there's about 15, 20. So you can definitely use H2O for some of these things. The GBM just works out of the box. Random forest works out of the box. GLM. Now deep learning, and we've put this to good use already. Actually, Joe Phi was at #1 here for a while, but then it was 500s or something a little later because we overfit. I did the same thing. I was in the top something in the beginning. Now I'm at 800 out of 1200. So I didn't do it right, but we have Mark here who actually plays better in this competition. So we'll learn more about how to do it right, because it's not just the tool, it's also the people, right? You need both. And our goal is to have good people use H2O to make the combination even better. All right, so here we are. Let's get back to the actual virtual image. So I would ask you to load the deep learning version of the, so the goal really is that everybody follows this along, and we all know that we can run these methods from the VirtualBox environment. So I ran something earlier, but it was the same thing, so you can just ignore that. Once we load the library, we have the methods available, so you can see that there's a lot of arguments to deep learning. Some of which are experimental, some of which are very important, some of which are not so important. And H2O Dev will go to great strides to make that easier for you to know which ones are important, which ones aren't, and so on. So the whole user interface will become nicer very soon. In the current version, in R especially, you don't know that, right? You just have a list of things. So that's why this tutorial will help you guide to get there. But also this booklet will help. Mostly you need to know the same three things that you always need to know: predictors, response, and what's the data frame. You can optionally give a key where you want to store the model under, but usually you don't need to know the key. And then one important factor here is hidden and activation and epochs. So these go together somehow. Like these are the really important ones here. However, activation is per default the rectifier function, which is just, it's a nonlinearity. It's straight and then it goes up linearly at 0. So it's something it's fast to compute. The derivative is easy. It's always 0 except when you're positive. So it makes the math a little faster. And when you have enough of those straight things, then you can make up any shape. So in the end, you can do really good models with a rectifier. You don't need a 10H sigmoid function, which is more expensive to compute. So I generally like rectifier, and have not seen a case where it doesn't work well. So the default is fine, you can say. So now for the number of hidden layers, that's how many neurons you have and how many layers of these neurons you have. So if you don't know what a neural net is, you should Google that real quick in Wikipedia. Basically, there's a bunch of layers of numbers, and they connect. So each number affects the next layer of numbers with a weight, from every one to every other one. And these weights are learned. And the more you have, the more resolution you have, the more layers you have, the more non-linearities you have, which means the more complex functions you can represent. So let's say you have to do the square root of something minus something else. To get that square root right, you might need 2 layers or 3 layers or 4 layers of hidden neurons, and not just 1 layer, okay? So just the more layers you have, the better it gets. However, the harder it is to train, because there's the issue of the diminishing gradient when you go back with the derivative. There's a backpropagation concept that is applied here to train. So you need to compute the derivative of like the error function, and you try to fix stuff so that the weights get better. It's stochastic gradient descent, right? And if you're trying to get better, you need to know the gradient. But if the gradient is 0, you don't know which way to go, because it seems like it's the same left and right. So the issue is really to find something that works. And typically it's 2 layers, 3 layers, 4 layers, that's about it. If you do it 6 layers, then you're pushing the limit already. I haven't seen the case where you needed 6 layers, except for maybe the last digits in 3 digits for Higgs. 6 layers is a little more accurate than 5, but you need to train much longer. So maybe 4 layers is actually the best model given the time you have, especially for production use cases. When you just need to have many models fast, you might want to use only 2 or 3 layers. So typically, make a couple of layers with a few hundred neurons each, and you're probably okay. And the default is 2 layers with 200 neurons. So that's easy and fast. runs about as fast as like a random forest or something, and you're getting a reasonable model. Now, epochs is the number of iterations over the data set. They're streaming point by point through the neural net, and every time it sees a point, it gets better. The neural net fixes itself to become better, and you can do as many passes as you want. It just gets better on the training data. Doesn't mean that it gets better on the validation holdout set, right? The generalization might be bad. It might be overfitting, as you said earlier. So you have to balance that. So you can give a validation data set, and then in the end, the model will actually be the model that's the best on the validation data set. Per default, it does the override with best model, which is somewhere here. That's enabled by default. So you might say, what's the default? I don't see it here in R. That's a good point. We don't have the defaults written here. The defaults are written in the manual in this yellow booklet, but they're also shown in the web API. So let's go to the web API to make sure we know that this is actually equivalent. So if you just go to the H2O GUI, and you say model deep learning, you'll see a lot of things here. And some of the things are pre-filled. And that's exactly the defaults. So if you don't know what the defaults are, the web UI is your friend. Of course, you can also look at the log file after you ran something, if you know where the log file is, and then follow all that information in there. And we'll get to that hopefully later. If not, then please remind me. I'll show you where the logs are. But basically, I'm giving you the bits and pieces you need to actually be practical with this, right? I understand it's not easy to see 50 arguments and then say, okay, good luck. But this next few hour or two should help figure out what's necessary. And it will not just be deep learning alone, it will also be multi-model scoring where we compare GLM, GBM, random forest against deep learning and have n-fold cross-validation on all of these. And we do grid search on all that, right? So in the end, you get a good model. So this train samples per iteration, that's an option that's actually important. And the default is auto-tuning, which means it spends about 4 or 5% of the time for communication. The rest is used for computation. That's only a concern for distributed systems. If you have one machine, it doesn't matter what that number is. You could say, as long as it's default, it's fine. If you have 10 machines and you have a data set with, let's say, only 1,000 points, and each machine gets 100 points, then it doesn't spend a lot of time in the computation, right? It only has 100 points to do, and then it says, what now? I'm done. My map is over. There's a way to say, okay, no, make 1,000,000 points your map. Make that map 1,000,000 points, and keep going through those 100 points over and over again. There's also a way to say, I don't want just every node to have 100 points, because my data set only has 1,000. I want them all to have all 1,000. And there is such a, sorry, the font size? Okay, sorry. There is such a way to say, use the same data set, the training data set, everywhere, if it's small. Replicate the training data. And that's actually the default. So if you have really, really big data, you need to disable that. At the bottom it says, here, replicate training data. That's only for multi-node operation. But if you have 10 nodes and you have only 1,000 points, of course you want all nodes to have all the 1,000 points, right? So there's little things like that, and those are explained in the booklet, but per default it should just work. If it doesn't, then you will notice, basically, because it will either be very slow or it will not give good numbers. Which in both cases you could say, well, deep learning doesn't work, and that's a concern, right? Or you could say, let me try to improve it. Or you can send an email to me and I'll try to help you. So there's a little bit of hand-holding required still, but not too much. I really think it's possible for all of you to just get a good model with a little bit of effort. At most, you need to read the booklet. That's about as much as I can ask, right? All right, so let's go here and look at the help. I probably will say it's a little small for that. So you all know R, right? Who has never used R before? Wow, okay, there's very few. Okay, great. So having R, you know, a help is there, and there's also a demo and a example and so on, so you can run all these things. So when we go up here, there's help, that's what we just looked at. All the options are explained, at least a little bit. That's roughly the same text that you also see in the web GUI on the right side. So it should be more or less consistent. There's an example. So the example we can run here by saying example H2O deep learning. And now we just ran something. So you can see here it was really fast. What it did was it says import the iris file. Iris is already in R, but we actually imported our own version here as a CSV from somewhere. I'll try to make it even bigger, but at some point it's going to be, all right, here we go. And then after the imported iris, this iris.hex, the hex extension usually means it's inside of H2O, not in R. So if you say, what is this object? It'll say it's an H2O data frame, or H2O parsed data, it's called. But it really should be called H2O frame or data frame. That object doesn't exist in R other than that it's a pointer to something that lives in H2O. And when we say, I want to do something with it, you have to do something from H2O, basically. So you have to tell H2O to do something with it. So all the functions that start with H2O dot something are the ones that work on those hex frames, because they will know what this hex thing is. It lives in the distributed KV store in Java, in this distributed Java context. So in this case, I said H2O deep learning. The first 4 columns of the iris data set are the predictors. Y is the response. And we used the 10H activation function and had 2 layers of 10 neurons and just passed 5 times over the data, okay? And this little model came down with an 8% training error. Now it says validation error of 1, which just means it's all wrong because there was no validation data set. So you could argue that we have to clean this up a little bit, which is probably true. H2O def will be much nicer than this. This is basically just showing you the REST calls response, which said, here's your model, and there's a couple numbers I'll give you. And somehow we have to say what this number is. If we had said it's nan, or missing value, you would say, why is there a missing value? If I say it's 1, you say, why is it 1? There's always something. Best probably not to print it at all. But then you might say, it should be more generic and always show the same thing, right? So we chose this path where we just show it even though it's not there. So you need to know that you didn't pass a validation data set, and hence ignore this. The confusion matrix that came out, well, it's 3 classes, so it's a 3x3 confusion matrix, and it shows up like this because I had to make the font size so big. But you can imagine that it works. All right, so let's go back. So everybody's comfortable running example.h2o deep learning, and now we can run, now we can run the demo. And for the demo, you have to press enter, and it downloads a prostate data set from the web. This is a more realistic data set in terms of categoricals and numericals and all that. Here you see it actually imported the file from HTTPS, which means you can just give an URL and it will get the file from there. That's one way to download data. Just point it to the web server somewhere. Doesn't have to be local, doesn't have to be Hadoop. Can be S3 as well. What came out of it was a binomial model, because we wanted to predict whether or not this person had prostate capsule, which is indicative of cancer. Let's see how we did that. So we said model building. Here was a H2O deep learning model. Again, yes. There were a few predictors. The second column was the response, and we again did 10H, but this time it was 3 hidden layers of 10 neurons each. So only like 30 little neurons that are connected with each other. So the weights are 10 times 10, another 10 times 10. There's 100 weights on each of these connecting matrices. There's each one bias. There's a couple more for the output units because it's a binomial problem. So in the end, it's a few hundred numbers, basically. That's our model. And with those few hundred numbers, you can almost memorize those 380 rows times 10 columns, but not quite. So this is not going to be a perfect model on the training data. And you can see there's still 3% error on the training. But of course, if you had more neurons or you trained longer, this would be 0. It will just memorize the whole thing. So there's a H2O performance call, okay? And the H2O performance call is the thing that actually tells you how, it's similar to the performance call in R. It tells you how good your AUC is, how good your classification error is. It also can tell you the thresholds needed for label making from the probabilities for best F1, for example, or best F2, for best accuracy, and so on. So in order to make a prediction with that model, you have to run it like this. You have to say prediction with model and data. That's intuitive. That's same as the R predict. And in this case, I actually pulled the data locally to the R cluster. Sorry, to the R server, this R instance here on my laptop. So I said as data frame, okay? So as data frame pulls it to R, and as H2O puts it up to the cloud, to the H2O server. So now we have predictions in R. We can look at them here. Actually, you can also do the head prediction, and it will still work even if you didn't pull it in first, because we overloaded the head and tail operators in R. So you can just try what works and what doesn't, and once you have seen enough examples, you kind of get a feeling for what's actually doable in H2O and what isn't. And if you find anything that you're missing, please let us know. I've been able to do a couple of Kaggle scripts, so I'm kind of comfortable myself now, but maybe I'm doing things wrong, or maybe I'm doing something in a way that you could do better if only you had this one function, right? So please let us know what you are missing. That's very important to us. So once you have a prediction and the actuals, then you can do this H2O.performance call. And you just have to give the probabilities, which in this case is the third column of this prediction object, because the prediction was for two classes. Prediction was labels, and then probability for class 0, and then probability for class 1. For all the classification problems, our predictions are actually n classes, probabilities, and then one more label in the beginning. That's our convention. So you always have to figure out which probability you want when you're actually asking the performance metric to score your prediction, because there, what matters is the sort order of probabilities. You want to know that the things that you predicted were 0.99 true were actually true or not, right? So those sort orders matter. So H2O.performance here got the prediction 3. And prediction 3, prediction is the version that's living in H2O here. That's the one that H2O made. So that's a hex object, if you want, that sits in the cloud. And train is also our original data set, and train 2 was column 2 of the prostate data set, which is capsule, which is what you wanted to predict, the labels. So the performance function wants probabilities and labels. In this case, we said the measure is F1, which then says, make me a confusion matrix based on the thresholds for best F1. So this confusion matrix could look different if the threshold had been chosen differently. So if you don't know what that means, go to the web page and run, for example, a model, say prostate. I can just run it on the web server here, say capsule. And let's just run the defaults. So that's 10 epochs on 200 by 200 neurons. And I just say go. Now it's building a deep learning model with 2 layers of 200 neurons each. Let me turn off the automatic refresh. Oh, it's already done. OK, good. So now we can go down. So there were 42,000 parameters in this model because it's 200 by 200. And then in the beginning, there were 8 times 200 input connecting weights, and then 200 times 2 outgoing weights, and then a bunch of like 1, 2, 3, 4, 3 bias values, I think. You don't need the bias for the input. So that gets us down to a 24% training error. And here's actually a link, scoring for binary classification. If you click on that, you'll get to this point where we explain what an ROC is, AUC, and all that. Okay? So whoever doesn't know these concepts, please go look. So this curve is almost this square blue line that I wanted, but not quite, because you haven't trained long enough. Prostate is a small data set, and passing over the data only 10 times doesn't mean that much. I still only have seen 3,800 points. So I can just say continue training this model, and I say, okay, train for another, why not 10,000 epochs? And now you should see the error go down. I need to disable this automatic refresh so I don't have to scroll so much. So if I do a Control R from time to time, oops, it already updated. So now it's like this, right? You basically memorize the whole training data because this is not on a holdout set. This is scored on the training data. That's the default when you don't give a validation set and when you don't specify n-fold cross-validation. So you can say, well, what does this mean? Well, it just means that deep learning trained well. It learned something. And the AUC is actually 1. The errors are 0. There's not one example that's wrongly memorized, which means we're done here. We don't have to train for 10,000 epochs. We only train for 620. It actually stopped early because 0 is good enough for training error. If you wanted to say it should keep training, for example, because you have a validation set and you want to do some dropout regularization and you want to keep refining the model, even though the training error is already 0, you're still thinking that you can make it a little better by smoothing it out a little, the edges here and there. You're still at 0% training error all the time, but you might get a better validation error. In that case, you would have to turn off this stopping criterion for classification. And there is such a value as well. You can also look at the model parameters here. It's just a little JSON display. There's one of these options here that turns off this early stopping. And in this case, it would be called classification stop. If you had set this number to non-zero, like negative, -1, it would have not stopped. Then it would have kept training for 10,000 epochs. All right, so let's do this thing again, and this time let's do n-fold cross-validation, because you don't really believe that we can get to 0% error. So let's do 5-fold. Do the same thing again. Oh, it's a checkpoint restart, doesn't have cross-fold validation. That's right, because I was trying to, earlier I started from a checkpoint, right? Because I already trained for 10 epochs, then I added a couple 10,000 more. At this point where I started from these early 10, I can't just start with n-fold now, because I was already at some point. So I have to go and delete this checkpoint restart. Delete that. We want to start a new model. We don't want to continue an existing one. And for this new one, we can now say 5 folds. And now let's also make sure we have the epochs up high. Good. So now it's going to train one model and then 5 more models to do 5-fold cross-validation. So first it trains one model all the way to 10,000 epochs, or until the training error is 0. In this case, it will also stop because training error is 0 at some point, and that's my model. And then it will do 5 more models, each on 80% of the data, and there's a different 20% that's kept out for validation of each of those 5 models. And those 20% pieces are scored on by each model that it didn't get trained on, and then it gets stitched together, and then you have 100% again. You basically have a prediction for each point in the training data that was made with a model that wasn't trained on it. And then you get your 5-fold cross-validation error by looking at how well that prediction thing is compared to the original data. Yes?
So is this
how you impute the data?
Yeah, if there is missing value,
Yes.
don't impute it. You can do it from 8 different ways.
Yes, definitely. Yes, sure, it will matter, yes. We also actually have an advanced section about that later where we do the imputation for missing values. And there's group bys and all kinds of stuff you can do with that. So now we go down. So now we see the classification error is actually not that great, right? It's only like this. This is the real error. And that's based on these 5 models. Each of those 5 models has been trained. Let's look at this middle one, for example. It has been trained on a train in the holdout split of 80-20. And it had this particular one had a 30% error. Some of the other ones were probably worse. In the end, we got to a 40% error. So this just shows you that n-fold cross-validation is useful, especially if you're a beginner, so to speak. You wanna make sure that you are having good validation.
So,
yeah.
Okay, so you had say 4 variables, right? In your model.
Yes.
Is there a way to change the order of precedence there for each of the models, which are the trainings?
Oh, the holdout splits? Right now, we don't have that. You would have to shuffle first and then do it again because we have consecutive pieces of 1/n.
So it's fixed now.
For all models except for GLM. GLM does actually the modulo approach where it does every nth, which both can have pitfalls, right? If you have the data sorted, then this approach doesn't work. If the other one, if every nth has a weekday order or something, you have a 7-fold cross-validation and you always get Monday.
Yes.
So there's issues like that, yeah.
Okay, and also see, like you just gave an example of Mondays and Sundays. Okay,
Right.
so is there a way to maybe it's in your future plans to have a like a weight? So Sundays give low weight, whereas Mondays give more weight.
Yes, point weights we don't have at this moment, but it wouldn't be too hard to write your own R script that makes a data frame based on that and do some munging and stuff yourself, right? You can always do it in R, you can do it in H2O, basically. It's just a question of how much you want H2O to do versus how much you want to do, right? So you have to find this balance. And H2O is really good at saying, make a column. You can do all kinds of operations based on that column on the other column. Like you can make a uniform random column, and then based on whether that number is more than 0.5 or not, you can take the point or not. So you can have your 50-50 random splits and all kinds of stuff. So you can definitely shuffle using H2O in a distributed sense without having to use R for that. Yeah.
Question, do you have any kind of model notebook or summary table of all the different models you've trained and the parameters you've changed and the results or outcome?
Yes. So if you go here, this is our interface here. It's a little small to see, but you go to score, you go to multi-model scoring. There's a list of all the things you did before, and then you can go to models, and you can see all the models that were trained. And you can see it if you say, it's a little small here, but there is a table here that compares all of them. So let me show you how this works. If I say, oh, not this one. Okay, you have to say first, you have to pick a data set to base your model selection off. Otherwise, you have too many different models that were built on different data sets and you can't compare. So let's say I want to compare on the prostate data set, okay? So now, there should be a way to now see the models that were built on the prostate data set. So these are the models that were built on prostate. I think I have to make this a little smaller for the sake of sanity here. So these are the models. The 9 models are compatible with prostate. Some of them are cross-validation models, so they themselves are not that great because they're only trained on 80% of prostate. But you can say it's still a model that was trained on prostate, so it's compatible. Now I can say view these models, and let's see. Now I think I can just select all of them. I think Prithvi would be better for this demo, but I have to just, let's say I pick these 3. There's a way to say pick only the ones you want and then score on these. Let's see.
I can chat offline. I didn't mean to derail you too much.
Yeah, I think there's a way, I've done it before, where you can select all the models that match a particular data set, and then you can say compare them or score them on a holdout data set that is also compatible. And then you compare all these models and their performance on that data set in a graphical way. And you can even make your own plots, for example, time it took to train versus accuracy, right? And then you can get your chart where you see GLM is much faster to get to a certain accuracy than, let's say, a random forest. So that definitely we have. And I think there will be more demos on that. I hope to do this again later when I have a better visual here. This is a little small inside of the Linux virtual machine. So basically, you can see that there's this web user interface, and this model was actually trained by me outside here, but it can also be trained from R. As you see, when I go to the admin thing here, jobs, there's a bunch of models that I didn't build. This one here, for example, was built by R, right, earlier by the demo. This was built on Iris. And you see here that the confusion matrix is actually Iris related. So you see the models, whether they're built by me or by R, it's still the same thing. The H2O server got the JSON request to build this model, and it doesn't care who wants the model, right? Whether it's R or you by clicking, it's the same thing. And if you wanted to see this in JSON form, you have to just replace HTML with JSON. And this is now the JSON response that you could query with a curl command or something, or with a different tool. And the same thing is true with Java. This neural net is now in Java form here, just because I typed Java at the top. And you can put this in production. The same with random forest or GBMs. You have all the trees explicitly out there without any heap allocation, so it's very fast. But yes, more to that later, I'm sure. The RStudio demo, here we go. We actually wanted to start doing some deep learning now, right? It's about time. So let's go in here and start loading the MNIST data set. Who has heard of MNIST? That's the handwritten digits data set. So it's a bunch of digits, 0 to 9, 28 by 28 pixels, digitized. And the goal is to figure out whether that digit is a 5 or a 7 or a 9. And sometimes these are ugly, right? Sometimes they're written really fast by somebody who didn't care too much. And your goal is pretty challenging to actually detect all these digits right. So there's always going to be a few that are wrong. That's what I mentioned earlier with the 0.83% test error. That's about as good as you can do without convolutions and distortions. If you just look at it straight and say, what's this digit? Even though somebody writes it in a diagonal way, and it's still supposed to be a 1, but it's written like this, it's difficult. If I could just rotate it, then my 1 would be much easier. So without rotations, it's not easy to pick it up right. But this is what deep learning does in this case. It just gets 28 by 28 pixels, expanded to 784 pixels. That's just my data set of 784 columns, and that's what I get. I don't have the opportunity to rotate it or anything. I just get it presented to me as the pixels were digitized. So this was the import file command. This easy to follow. Anybody has any questions, please let us know. So now we're running a deep learning model on MNIST. And who's following me along right now on their laptops? That will be the goal, that you all follow this. Unless you're already an expert user. In that case, you shouldn't be doing this here at all. You should be working or something. Okay. All right, so let's look at the model. The model itself says it has 11% error on the validation data, because I did pass the validation data set here. And I only trained for 0.1 epochs, which means it's out of the 60,000 points, I chose 6,000 points randomly and just passed through those. That was one pass. And I basically got lucky to see the right points or not. My confusion matrix is somewhat diagonal, but not perfectly diagonal. but still not bad, 90% correct, right? After passing only through a tenth of the data set. So clearly I didn't just see ones or sevens, I already saw all of the digits, otherwise they wouldn't look like this. And the data isn't sorted, and I was shuffling anyway when I did the 0.1% and the 0.1 epoch subset. This was a 50 by 50 model, by the way, so a very small model. Now we can look at the confusion matrix separately. It's going to be the same thing. We can look at the validation class error. These are just members of these R objects that are returned, or slots if you want. So DL model, you can do add, and then you can do tab expansion here again. The tab will show you what the options are that live in this object. So you could also ask, for example, the key. Say, what's the key? Make that a little bigger. Or you can say, what's the data? The data would be the training data, and it will show you the training data, or at least the head of it, the first few instances. All right, so we were stuck here, looking at this initial model. Now let's make a prediction. So again, h_predict, and I have to get the labels out of the prediction, the first column. So I say, comma 1 here at the end. These are the labels, and then the actual labels are the last column in the test data set. And now I can make a confusion matrix out of it. And that confusion matrix is what we just saw earlier. So I just confirmed that the model reported its own validation error correctly. And we can also, of course, do this kind of stuff where we have true everywhere for every field in the confusion matrix. So these are just lists in R, or matrices, or whatever it is. It's just, these are just small objects that live in R right now. But they're built based on a JSON response that came back from H2O. And those are built in Java, right? Java makes those JSON objects. All right, so we can look at the model parameters. And here we have the whole list. So for example, if you did a grid search and you had a winning model, you could ask what was your parameters. And you can reuse that for another piece of your R code later on. You don't have to look at it manually. You can automate the whole process. So let's do this now. Let's do a grid search where we automate this parameter finding. So a grid search is actually fairly easy to do. You just have to specify more than one argument for a specific parameter. So for example, in this case, the hidden ratio, the hidden layers, there will be two such architectures. They'll have a model with 10 by 10 and the model with 20 by 20. Okay? These are two different neural nets, and we just list them. And in this case, you have to use a list because you already used the vector C notation for the hidden layer itself. So if you have multiple of those, you can't just do a C of a C. You have to do a C, and then a list outside. But for example, for the L1 penalty, you can just do a C 0 and 1 10 to the minus 5, and that will give you these two things. So how many models will be trained here if you run this command? Anybody have any ideas? 4 models? Yes, that's right. 2 by 2. Okay. There's no n-fold cross-validation in there. If there was an n-fold in there as well, it will be a little more difficult, right? Then each one of those would have been an n-fold model as well, which actually would work. All right, so let's run this. And we can go to the web API and see that this actually is running. Just to be sure, we go to the jobs, and we see here a grid search being launched. And there's all these models. And now you wonder what happened. Well, actually, we forgot that there was also 10H and rectifier. It's 2 more. So it's 8 different models. See, we had 2 times 2 times 2. I got it wrong too. All right. Good, so we have 8 models, and let's see which one won. And you can go here in the web API. Oh, sorry, don't do that. You can go to the web API and see the top model here. Oh, the last one isn't done yet, so let's wait. Control R. Okay, so here, there's one model that has 12% error, the other has 24% error, so it's pretty big difference. Which one is that? It's the one with 2020, not surprisingly. It's using 10H, which has a little more resolution than a rectifier because it's nice and smooth. And it probably had no L1 because at this point, we're not yet worried about overfitting, right? So it's better not to do any penalties just to get a good accuracy real fast. But of course, if you did a real model, L1 would probably be the better model. So we can now see this result from R. We can say grid search. That's the name of the model. But actually, it was a grid search. It was a list of models. So grid search is a list of models returned. And there's 8 models in it. And you see the same order here that we saw on the web API. And grid search of model 1 will be the best model. Is this clear? This is a list of models, and it's sorted by the prediction error. Yes?
Just like you do the number of hidden layers, you also need to do the number of epochs. So they kind of, you can do all kinds of stuff.
Yes, you can do 50-dimensional hyperspace, right? Optimization. And actually, the next mini section will go into that a little bit more. So the best model that I extracted here with model 1 looks like this. It says I got a 12.3% validation error.
Quick question. How did you switch over to the GUI?
The GUI. I clicked on the icon on the desktop, but that actually got you to localhost 54321, which is the default port.
Comparison. Sorry, the grid comparison.
Oh, the grid comparison, how I found that. That was in admin jobs. Here, admin jobs. And if you don't know where admin is, then it's probably because of this here, right? Every time it goes to be too big, you have to go to the right side to get it from here. Okay. We can also do a water meter, for example. This is a little meter that says how busy our CPU is. We can also do a lot of other cool stuff that you saw earlier, maybe profiler. Right now it says there's not much going on. It's just network sockets waiting for traffic. You can do a network test, and it tests itself. It can send 6 gigabytes a second to itself.
One more question.
There's a log file that you can query as well. Yes?
You mentioned that it sorts by prediction error on the grid search here. Is there any way to suppress that sorting?
No, you would have to manually loop through it and do your own extraction to sort by a different criterion. I think GLM does not sort, so at some point it will be more consistent, but right now you have to be a little bit careful because we don't have too many of these pre-cooked functions that just do the right thing for you, but we're working on that heavily right now to give you this, let's run everything and see what comes out, basically. And the goal is by the end of this week at the latest to have that for everybody so that whatever you do, you get the right numbers back. But you have to be a little careful to cross-check certain things like that, yes.
In the confusion matrix there, you have 10 bins of the forecast and actual. Mm-hmm. Do you have anything like a cost-profit matrix that you can put, like maybe the top 10% is worth 10 times as much compared to the next 10% or something like that? So you have unequal weights, and sometimes you're spending money, so you could lose money at the lower decils.
We have hit ratio, and we have lift for binomial models, so that's the only pre-cooked things we have right now.
Okay, so no weights for type 1 versus type 2?
No. So now that we have the best parameters, because we just extract them from the best model, we can look at the activation function, the hidden layers, and the best L1, and that confirms what we saw from the web interface. It's just what we saw. So now there's the concept of grid search, and there's the concept of something like random parameter search, where you just throw numbers in intervals specified from min to max. Let's say L1, I say between 0 and 10 to minus 4. Find me something good, right? And I don't want to say try 10 to minus 6, 10 to minus 5, 3 times 10 to minus 5, and so on. I want to say just find it for me. So what I'm doing now is I'll do a random search where I have a loop. And I'll say do 10 times a random pick in this hyperparameter space in certain intervals for each parameter. So in this case, I will say sample from this vector of two things, either tanh with dropout or rectifier with dropout. Pick one of the two. Then the number of layers could be 2 or 3 or 4 or 5. Just pick one of those. I don't care which one it is. The number of hidden neurons for each of those layers that I picked. I don't know how many layers yet, but for each of those, just pick 10 to 50 neurons. Maybe a network topology like this is better, or like this. Doesn't have to be parallel, right? For L1, I say sample something between 0 and 1. 0 and 10 to the minus 3. And L1, also just one number. That's why there's a 1 here. Make me a vector of size 1 with values from 0 to 10 to the minus 3. And basically, I make a random number, right? And then the same for dropout. I'll say for all the layers, all the hidden layers, I want a dropout ratio between 0 and 0.6. And dropout just means that some of my neurons will be zeroed out. But that's for every single point that gets trained, a different subset of neurons is deactivated. It's the same thing as saying I get blinded a little bit, just like now when the lights are shining in my eyes. I don't really see what's going on over there, but I still have a good idea that there's people walking or something. So I can still see what's happening, but I'm not overfitting to that particular person over there. So the same thing is with dropout, right? So I can say, let's try different dropout ratios. And the same for the input dropout. I also want a value between 0 and 0.5 input to be dropped out. And of course, this wouldn't make sense for most data sets to drop off your input, but if you have something like MNIST where you have 780 pixels, and they're somewhat noisy because you don't know how it was written and all that on a piece of paper, maybe it's a good idea to not see all the neurons, not see all the pixels, and not fill up all the neurons all the time, because that might lead to overfitting. That's actually what helped to get to this world record number. So this model now is built with all these parameters. And then we add this model to a vector. In the end, we have 10 models. Okay, so let's run this. This is now a real grid search improvement because it's using random parameters. One model, 2 models, and so on. And you don't know what the models are, right? Some of them are 2 layers, some of them are 5 layers. It could be slow, it could be fast. But of course, this is just a toy example. But this samples this high-dimensional space because I have a bunch of different things here. I have the number of which activation function, how many layers, how big are the layers. I have L1, L2. I have dropout for each of the layers. I have input dropout. So it's in the order of more than 10 parameters that I have to be optimized. And in a 10-dimensional space, grid search that you humanly pre-select is not as good as random search. So this will help find a better model faster. So what I'm doing here now is I just do a brute force loop. I'm sure somebody with R skills better than me can make this better. I'll just loop through it and say, if you're better, then record that. And now show me what's the best. So the best model has a 12% error still. That was my original model I built. Nothing improved. So if I go to the web API, because I put the original model in there as well. If you look at, for example, this model here, this is one with 50 and 38 and 21 hidden layers and has some L1 and L2 and some weird dropout. It's all random, right? It's not necessarily the best idea to just go brute force with random numbers, but it shows you what you can do. And this wasn't as good. It was 14%. So my original model is still the best. But it could have been different. And in your case, it actually might be different. Who has anything better than 12%? Okay, great. I was expecting something like 11 maybe. Anybody? You got 11? Okay, cool. So you wonder, why did you get something different? You have the same virtual machine, right? That's what's going on. Well, that's because deep learning is using multi-threading to be faster. And it's using all these threads at the same time to run and train its points. Each thread gets different points to train, and it updates the weights. But there's only one set of weights per node. So this instance of H2O is a single node instance that node has one model, but it has 4 threads running. And those 4 threads will all write to the same weights and read and write and change the same weights. So in the end, those 4 threads are competing with each other. Who can get the read and the write done faster, basically? While I read, you override it, and then I write, and then you read, and all that. And it might not be done like perfectly in a locking way, but that's a good thing. We don't want it to lock. If you had to lock every time one of those threads was writing, on a 32-core machine, you would never get the speed ups we're getting. And usually these overwrites or these wrong reads, let's say, are not that bad because you're not changing it that much. You're just doing a little correction. And overall, it's worth it not to do the locking, but instead do a faster update. That's called hog-wild. And that paper was a breakthrough to show that you don't need to be that strict, basically. But you could wonder, well, I need to know what's happening. Well, sure. Then we added the reproducible mode that says if you set reproducible equals true, then it will be using single core operation and it will be the same number. But only for small data sets. For really big data, you wouldn't want to do that anyway. Yes?
So when you do the grid set, so for each set of that grid parameter, it's doing this hog-wild approach?
Yes, yes. Each single deep learning model is a hog-wild model because it was built in parallel. So we're not parallelizing over the grid search parameters, we're parallelizing over each model itself.
So then that error basically is reproduced for any...
They're serially built, actually. The models are built in serial right now. Yes?
With that type of paradigm, we have some type of stochastic noise associated with that. Is there any way to give some type of error variance? So if we have accountability,
You have to run 10 models, right? And then look at the standard deviation, basically.
Right.
There's not much else you can do, I think.
all right, thanks.
Sure. All right, so the best model has parameters and the activation function, and the best parameters are still going to be the same as last time. All right, so now that we have this model, you might say, well, I don't want to just waste it and remember what the parameters were and start a fresh model. I want to just continue building the model, right? That's what we did in the web interface earlier. So I'm going to do the same thing here. I'm going to run a model, and I specify the best model as a checkpoint. So I just say deep learning, same number of predictors and response, same data, same validation, and I give a checkpoint. And you have to be a little bit specific here. You don't want to give like nothing and just say continue, because this thing allows you to change certain things. Like L1, L2 you can change. You can train with 0 L1, L2, and after a while you notice you're overfitting, you can turn up the L1, and suddenly it gets better for validation set, right? You can do all these tricks. So you don't want to just say continue. You want to say continue, but use this L1, this L2. So there's a couple of parameters that I listed here that you want to specify if you're changing them from non-default values. In this case, it's L1 and L2. So you can just use the best parameter object we made earlier and just get its values. You don't need to remember them. You make it generic like this. So we continue the model from the best model with the same L1, L2 that was deemed the best. And now it's done with that. Now let's look at the error. Now it should be, oh, happened here. Oh, I got the wrong line copy pasted. Okay, here. So the error is now at 8% because we added another half epoch. Okay, that's good. Now we can say that's good enough. I don't need anything better than that. Let's save the model to disk. So I'm just writing into /temp. And force means I overwrite an existing file. So this model is now serialized out. This model is the Java objects that are living in the KV store is now dumped to a file, the raw bytes. So if you come back in a year from now and say load it into H2O, there's a big chance it will not work, right? So in this current moment, you have to remember what version of H2O you were running. In this case, it's Maxwell 8. It's this current latest stable release. There's a good chance it might still work in the next stable release, but another later one or so might not work anymore. So at this point, we're bound to versioning with a binary dump, and that's not great. But it's better than not having it. And next version, the H2O-Def, will have a better way to serialize models. It's going to use a really good versioning system. So let's say you kill your R session and you start it up again, your H2O as well, you kill it all. You come back and you just go from here after you initialize the cluster and you load the module on that. Then you can just press here, load it, and you get this load model call to actually get the bytes from the file and dump it into the KV store, and that's your model. So you can just continue. So in theory, I could give you the world record model for MNIST, and you could verify that it actually has the 0.83 test accuracy. And now we can say, okay, well, I want to train some more. Let's train some more on that model that we just loaded. Another half epoch, and now we are at 7%. Okay, so you just see how it gets better every time. And these are the parameters you need to run to get to 0.8. Let's make it a little smaller. So you see for 0.83 test set error, all you needed was rectifier with dropout, 3 layers of hidden, 3 hidden layers, 1,000, 1,000, 2,000. 2,000 epochs, a little bit of L1 penalty, a little bit of input dropout because you have too many noisy pixels. You don't want to see them all at all times. And the rest is basically defaults, except that I said don't stop when your classification is at 0. You want to keep training even though you're already at 0% training error. Maybe you get better at generalizing. And I also said the train samples per iteration is -1. That's a specific option. That's not default. Default is -2, but it shouldn't be that different. I think both would have worked just fine, but -1 is for saying that all nodes pass through all their data, and that's it. And in this case, I replicated the training data, so all nodes go linearly through the whole data set every time. There's no sampling going on. So maybe that's a good thing, maybe it's not so good. Maybe it would be better to do bootstrap-style sampling each iteration by specifying a different fraction of the data set instead of all of it. So there's a little tuning parameter here, but in this case I said everybody go through all the data. At least I'm making sure I train well. And that was this confusion matrix here of 8.3. You see that a bunch of 2s and 7s are confused. And there's not much you can do unless you make a model that's better at those two specifically, right? But then it wouldn't be a single model anymore. All right, and the regression is the same thing. I can say make a regression model out of it because the response is 0 to 9. Might as well be a number to me instead of a class label. And I turned off classification with classification equals false. If you give me a double valued response, of course, that's all I can do is a regression. So by default, it does the right thing. So the regression model now shows a mean square error of 2 point something. And these two numbers can also be queried from the model itself. And we can confirm that by making a prediction on the test set and then subtracting the actual label and then squaring it and then computing the mean. That's done in H2O because there's H2O.predict operates on a H2O frame and mean is overloaded to actually do it in the H2O side. So this is one instance of, it looks like R but isn't. This is actually done in H2O. And this can operate on a big data set. And we also have an H2O.MSC function, which is the same thing. It's just a little helper object. So you don't need to do the square of the difference. So the next thing is cross-validation. You can just specify n false equals 5. And now we'll get a better feeling for what happens. But as you know, the test set is pretty good as an indicator of how good you are in MNIST. So it's not that small data or so. It should be roughly the same order of magnitude. So the model's validation class error, in this case, is the n-fold validation error on the training data. But we still call it validation error because there the main model that is built in this n-fold cross-validation. There's 6 models being built, even though fold is 5. Right? One model is on the whole training data, and then there's 5 more on these holdout splits. And the main model has a training error. And that's just how good it is in overfitting on itself, basically. And then there's these 5 extra models, and those stitched together predictions are then used to score on the training data how well it's doing. And that's the n-fold cross-validation error. And that we report as the validation error. So when you look at the validation field, that's the actual n-fold cross-validation number. And there's a GitHub R unit test. There's a link there that shows that this is correct, basically. What it does is it does a loop in R where it cuts it up like in these 80%, 20% splits, and does individual models and then predicts on those and stitches this back together and so on. So you can confirm that what we're doing is correct, but the n-fold cross-validation is basically done the hard way right now. We just make 5 new models in addition to the one model. All right, so you can ask what's the list of the n cross-fold models. This DL model XVAL is actually a list of a lot of models. All these 5 models are listed here. They all have a training and a validation error on their 80-20 splits. And you can look at each of those functions as validation errors, and you see they're all around 12 or 11%. And now you can combine grid search and n-fold by doing it like this. You just specify a grid search, 2 different activation functions, and n-fold, and then the whole thing will run as many models as the grid search set, and each one of those itself has 3 models being built, 1 main model and then 2 cross-validation models. So once you know that the model that you want to pick is like this is the best one, for example, then you can say predict, and it will predict with the model that was trained on the whole training data, right? It reports the score based on holdout cross-validation, but the model itself was actually built on the full training data. So you don't need to go back and retrain a model on a full data set with those parameters. You already have that. We just built extra models to score. So in this case, you can see that this grid search model has 2 different outcomes. One is 23 and one is 31% error. That's because it's only a 10 by 10 hidden neuron model. It's not that great. We also have variable importances. You can just say variable importances equals true. And then you'll get variable importances for MNIST, which pixels matter the most. Not as meaningful here maybe, but you can get the idea that this extends to features with categoricals and all kinds of stuff. There's also a paper cited that says how it's done, so it might be interesting for those who are interested. It's not trivial to do variable importances, especially not for deep learning. And there's this, what I have here, I think, is automatic learning rate. I said it's always just correct. You don't need to worry about it because it just always works. But there's still a little bit of room for tuning. There's epsilon and rho, 2 parameters that determine the adaptive learning rate. And one is basically saying how fast you go into local minimum, and the other one is saying how much you want to care about the global space, like your momentum if you want. So those 2 we have to balance a little bit. But the defaults are pretty good. That got us good numbers for both Higgs and for MNIST, and for eBay as well. So there might be space for optimization by doing this here, this loop over a couple of rhos and epsilons, just to get an idea of how they converge. So here I have a lot of different cross combinations, and I see the error goes from 18% to 80%. So some combinations are really bad because we're not converging fast enough. But maybe it would have been the best model in the end if I had waited for 500 epochs instead of 0.5, right? So you can't just say, oh, that's the best epsilon, I'm going to use this from now on forever, I'm done. You know that as soon as you change one other number somewhere, it's all over again, right? So you have to get some feeling for this, or you just pay the price and buy a bigger machine or wait a little longer if you really care. So there's a bunch of little tips and tricks at the end that are just written in text. They're not actual code to help you with how to treat missing values, reproducibility, categorical data, early stopping. I mentioned some of those things. There's the number of validation points used for the validation error that's reported is all the points in a validation data set. But if you have a terabyte data set and you have 100 gigabytes to validate, might not be a good idea to do that every time after every map reduce, you validate on 100 gigabytes. So I built in something that's called score duty cycle or so that says only 10% of the time you actually score. And the first time might take an hour, but then it will wait 9 more hours before it scores again so that you don't waste too much time scoring. But if you know already that 100 gigs is too much for your statistical sample to score, you can just specify that it should be only 1,000 points or 10,000 points. So that could help with the speed. It's called score training samples and score validation samples. So it basically samples for you as it builds the model. You don't have to worry about it yourself. And there's a little benchmark against the R package called NNet, but we don't have to go there. I think it's an overview. If anybody has questions about deep learning, now would be the time. There's more tonight and tomorrow, of course. Yes? Yes, compared to the GPU version, a single CPU, like a single laptop, let's say, is slower than a GPU, right? If I give me a Titan NVIDIA CUDA card with Theano, then Theano will be faster. But if I have a cluster with 20 nodes in Hadoop that all have 32 cores, then maybe I'm faster. So it's a balance of what you have and what you want to do. If all you want to do is deep learning on large images, let's say, then a GPU solution will be better. If all you want to do is do modeling, data science, compare GLM, random forest, GBM in one framework, and run stuff, then this is better. And I yet have to see claims that this is slow. I actually think it's reasonably fast, but I would love to have a benchmark study comparing this against actual. If anybody here is using other products, let us know. It's already optimized. We have like Fortran-like speeds on the matrix vector multiplications and so on. So it's not slow, but it's as fast as you can do with CPUs.
So getting to the autoencoder nets or freezing hidden layers before you train the next one. Is that something that's in process in like the next quarter, 6 months?
Yes. So the stacked autoencoders, we're going to talk about anomaly detection and autoencoder in general later.
Okay.
But there is no such thing as stacked autoencoder right now.
Okay.
But it wouldn't be hard to implement because it's a couple of learning rates set to 0 somewhere, right? Basically.
Right.
Yeah.
Yeah.
Okay.
Okay.